We're advancing now from talking about the magnetic force on individual moving point charges to the magnetic force, the net magnetic force on a collection of zillions of moving point charges, on a whole current, in fact, through a wire. So, what does happen when you have a current carrying wire, like this orange copper wire here, in an external magnetic field, such as that created by this horseshoe magnet here? One of the things that occurs is known as the Hall effect. So this is a wire carrying a current perpendicular to an external magnetic field. This is the B field created by this other magnet, not the B field created by the wire itself. We'll be largely ignoring the B field created by the current itself in the discussion that follows. So the Hall effect is that in this scenario, the wire will develop a potential difference across its width. From there to there will be a potential difference. Let's see why. Okay. So this will be our wire here with a current traveling upwards in that direction. So we've got an electric field driving that current upwards. So these are the edges of the wire, and the blue dots indicate that this wire has been placed in an external magnetic field that's pointing out of the page. So I want to consider the motion of free electrons inside this conductor once this B field is in place. So if our current is traveling upwards, then that means we actually have electrons coming this way through the wire. Let's consider one of those early electrons, one of those first generation electrons moving through this wire not long after this B field appears. So, okay, here's one of those electrons, negative charge. It'll be moving down. So with some drift velocity downwards like that in the presence of this B field. Okay, the magnetic force on the electron, QV cross B. Okay, V is down, B is out of the page. So that points left, but Q is negative, so that flips our magnetic force to point right. So this electron will be feeling a magnetic force FB to the right, causing its path to curve until it sort of collides with the wall over here, and it'll end up kind of stuck on the wall right there. And it won't be the only electron that this happens to. There will be zillions of free electrons in here, and all of them drifting with that drift velocity are going to feel magnetic forces that drive them over to the right-hand wall of the wire. And before long, we're going to get a buildup of excess negative charge on that wall from all the electrons being pushed that way by magnetic forces. And at the same time, over here on the left-hand side, there will be electrons all drifting downwards, but then driven to the right by magnetic forces, driven away from the right-hand wall. No electrons will be driven towards that left-hand wall. So we're basically going to be left with a deficit of electrons, free electrons over here, an excess positive charge over here on that left-hand wall, where the positive ions remain, but electrons have been driven away by the magnetic field and not replaced. Okay, so that's what's going to happen to our first few generations of electrons. We're going to get these buildups here. Now, some later generation electron is going to see a different scenario. If these buildups are already in place, and if they've built up to the extent that they're now creating their own strong electric field component, if there is now an electric field contribution pointing from this line of positive charge towards this line of negative charge, let's call this E prime, to distinguish it from the original E naught that's driving the current in the first place. These layers of charge are now building up E prime, a secondary electric field perpendicular to the original electric field. And so some later generation electrons are going to be feeling forces from this secondary electric field as well. So our charges will build up to the point that this secondary electric field is strong enough that some later generation electron coming along will feel a net force that is once again zero and will be able to drift with our drift velocity in a steady state current down the wire. Let's draw the FBD for this later generation electron. First off, from this original electric field, that gives us this big electric force that's driving our current. That's, of course, being balanced by the drag force in this medium. So there's our dynamic equilibrium that we're accustomed to. But in the horizontal direction here, or the left to right direction, there's going to be a secondary electric force here, Fe prime, from this secondary electric field pushing that electron to the left. The charge buildup will continue until this secondary electric force has grown to be large enough to balance this magnetic force here that's still present because our electrons are still moving in this external magnetic field. So this Fb that was pushing all those electrons to the right originally, that Fb remains more or less constant in size, but this Fe prime grows until it balances that Fb. Once that happens, electrons will no longer be piling up on the right-hand side. We'll end up with this sort of a steady distribution over here, and these late generation electrons will be able to drift right on down the wire in dynamic equilibrium, both in this direction and in that direction. So this actually represents our final steady state scenario. And the condition that we've got here is that the electric force due to that secondary electric field will grow until it's equal in magnitude to the magnetic force that was pushing those electrons to the right in the first place. So this expression here will be E times our secondary electric field, E, the magnitude of a charge on one electron, equals the magnetic force on that one electron, so that's its Q, E V cross B, so V is our drift velocity. Our drift velocity and the B field are perpendicular to each other, so our cross product results in just the product of the magnitudes of our drift velocity and the magnetic field strength in this region. And we see that little e cancels out, and we can compute the strength of the secondary electric field necessary to balance out the magnetic force from the external magnetic field. Okay, so what we're noticing here is that due to this buildup of charge on either side of the wire and this electric field across the wire, there's actually now a potential difference across the width of our wire. Not just a delta V in this direction, high potential down here, low potential up here that's driving our current that way. We also now have a higher potential on the left from these positive charges than on the right from these negative charges. So high potential here, low potential here. So there's a delta V across the width of the wire. That discovery is known as, this buildup and this voltage across the wire is known as the Hall effect. And that voltage is known as the Hall voltage. Named after Edwin Hall, an American physicist who discovered this in about 1879. Okay, so if you were to set up a voltmeter attached to either side of the wire here, with one probe at the right side and one probe at the left side, you'd be reading a potential difference across the width of the wire. This would be the Hall voltage. Okay, let's find an expression for that Hall voltage there. So this delta V H for our Hall voltage, that should be the potential at the high potential side here minus the potential at the low potential side over there. So V plus minus V minus, V here minus V there. The opposite of the integral of our E field in this region. And our E field in that region will be the sum of the primary E field plus our secondary E field minus those dot dr as we go on a path from the negative side to the positive side. So our path here would be starting here and integrating to there for our path integral. Okay, if we make our path actually just straight across, then that path is at a right angle to the original E field, E naught, at all times. So E naught dot dr will be 0. They're at right angles to each other. But E prime, pointing to the right, is exactly opposite our drs or ds's pointing to the left. So E prime dot dr will give us a minus sign for those two vectors being opposite in sign. That minus sign from this dot product will cancel that minus sign right there. So in summary, we'll have E naught dot dr from negative to positive. That dot product there goes to 0. And then plus our E secondary times dr. Since that dot product negative and that negative cancel each other out. If E prime is relatively uniform across our wire here, then this just becomes the magnitude of E prime, sum up the dRs, or the ds's, we sometimes call them, all these little steps along that path, a little dr or ds, and we sum up all those and just get the width of our wire right here. Let's call that W, the width of our wire. So this is E prime times the sum of all the dRs, which is W. And this is known as the Hall voltage. I guess I have 2 points to make about it. One is that this is a useful phenomenon because it enables us to construct a device that we could use to measure the strength of magnetic fields, a device called a magnetometer. I'll diagram that in a moment. But the second interesting point about this is that this discovery of the buildup of a voltage across a current carrying wire in an external magnetic field, it proved historically, definitively, that when you have a current traveling through a wire, it is the negative charges that are carrying the current. The negative charges are moving, and this proves it. It proves that, in particular, positive charges are not in motion when current is flowing. Only negative charges are in motion. Here's how it proves that. Suppose you were hypothesizing that when a current flows, there are positive charges that are in motion. Well, if that were true, then we'd have some positive charges entering from the bottom with some velocity upwards. And you could put that wire into this external magnetic field, and there would be a magnetic force on those moving positive charges. So V cross B would give a force to the right on those moving positive charges. There would be a magnetic force like that, causing your moving positive charges to arc over and pile up on the right-hand side of the wire. So if positive charges were carrying the current, we would get a high potential on the right and a low potential on the left. But that's not what we observe. We observe just the opposite. We get low potential on the right and high potential on the left. Therefore, it cannot be the case that positive charges are in motion inside a wire. The Hall effect proves that current is being carried by negative charges. Only negative charges are in motion. The background positively charged ions, the copper ions in the background, they're not moving, and so they feel no magnetic forces. Only the moving charges get shifted over by the magnetic forces. Okay, so that's a note of historical interest. This proves that current is carried by moving negative charges. Okay, now how can this concept be used to build a device that we could use to measure the strength of magnetic fields, a magnetometer? A magnetometer, magnetometer. Okay, let's kind of draw a picture here. Imagine some conducting bar instead of a wire with circular cross section. Imagine instead like a conducting bar with a length to it and a cross-sectional area and a width W. And let's attach it to a power supply. There will be some resistance in that wire, of course. Here's our power supply. And let's stick an ammeter along that wire to measure the current there. Okay, so we'll have a current driven by that power supply through this wire and a current coming down this way. Here's our EMF. And furthermore, let's have a voltmeter set up to measure the voltage, the potential difference across the bar. Here this wire is just hopping over the other wire, so they're not actually in contact there. So our voltmeter is probing the difference in potential on either side of this bar. So this voltmeter is exactly this voltmeter right here, probing the potential difference on either side of this wire. Okay, now enclose all of that inside some handheld device. Handle there, and let's grab onto it here. Okay, there's our hand holding our handheld device. And now if you wave this device around, and in particular if you place it into a region where you're expecting there to be some external magnetic field, you hold it with a proper orientation so that our current is running at a right angle to that B field, then we will get Hall effect across this bar right here. And we'll measure the voltage, the Hall voltage with this voltmeter. We'll measure the current with this ammeter right here, and your device could take those two measurements and spit out an estimate of the strength of the external magnetic field that you're waving your device over. Let's finish carrying out those calculations by combining our results from up here. Our Hall voltage depends on that secondary E field strength, and our secondary E field strength is proportional to the magnetic field strength. So putting those together, we have here that our Hall voltage equals our secondary E field strength, which is our drift velocity, times the magnetic field strength, and then times the width, W, of our conducting bar. And here we would bring in, say, our Nevada equation, where our current is proportional to the number density of free charges and the drift velocity and the cross-sectional area A, this cross-sectional area right there, of our bar. So let's see, let's sort of solve this for our magnetic field B. B will be equal to our Hall voltage divided by the drift velocity divided by W. So our Hall voltage divided by W divided by our drift velocity, and our drift velocity equals I divided by NEA. So I over N times E times A. And so here our device, our magnetometer, could measure the Hall voltage right there. It could be measuring the current running through this sort of test circuit right here. Measure the current. And if you know the width of that bar inside your device, and you know what the bar is made of, so you know the number density of free electrons, and you know the cross-sectional area of your bar there, then essentially this device can be used to measure the strength of the magnetic field that you've placed it in.